All right, good afternoon, AP Stats. Let's start off by going over the combining random variables exit ticket. All right, so remember whenever we're combining two sets of random variables, the mean is easy. If you're adding, add the means. If you're subtracting, subtract the means. This is the easiest stats can get. Alright, standard deviation is a little trickier. Alright, so with standard deviation, we are always adding. We never subtract. That's because standard deviation measures like variance or uncertainty, right? We don't actually know what the true value is of the mean, and so we're saying it's in a range of numbers. So when we have two different probability distributions and we're combining them in some way, whether we're adding or subtracting, we're adding to the uncertainty. So I'm just going to put variances always add. If I could spell the word always, that would be slightly impressive. Alright, variances always add. Remember, variance is standard deviation squared. So what we're going to have to do is square the standard deviation of the first random variable, and I'm just using x and y to represent the two random variables. So this is us converting them into variances, adding them together, and then to get it back to a standard deviation, we're going to take the square root, because standard deviation is the square root of the variance. So we can use this little formula every time and just drop the two standard deviations in. Alright, so I'll reference these in a second. Alright, number one, science majors in college pay an average of, so let's see, I'll use yellow for science, standard deviation of 130, I'll use green for English, they pay an average of 465 with a standard deviation of 90. Alright, the question is asking what is the mean difference in standard deviation between the amounts. Alright, so that word difference, what are we doing? Are we adding or subtracting? Alright, we are subtracting. So we need to find the mean and the standard deviation. With the mean, we just subtract the means, right? So I'm going to do 650 and 465. So 650 minus 465. Can't believe that took me so long to find. 650 minus 465. Alright, 185. Alright, so looking back, I can eliminate A and E because my expected value of the difference, which is a notation for my mean, is 185. Alright, remember with standard deviation, we have to convert them to variances and add them, even if we're subtracting. So I'm just going to use this little formula right here where it's the square root of the first standard deviation squared plus the second standard deviation squared. And I'm just going to drop in my two standard deviations, 130 and 90. Alright, so let me go back to Desmos and just put it in just like that. Not Amazon. Alright. Oops. Alright, use this to get my square root. Alright, and I just dropped those numbers in, 130 for the first one, and 90 for the second one. Alright, and I get 158.11, which is answer choice C, that 158. Alright, and I'm just going to keep using these rules throughout. Alright, question number 2. An auto dealer pays an average of $8,750 with standard deviation of $1,200 for used car trade-ins. So let's use yellow for the used car trade-in. Standard deviation. Alright, and sells new cars. We'll use blue for new cars. Average of 250,000, standard deviation of 3,100. Assuming independence, remember we have to assume independence, that's part of our conditions. of trade-in and new car prices for customer. What is the standard deviation of the revenue? All right, so this word revenue is okay, the revenue is saying how much money are we making, right? So if I sell the new car, it's the new car price minus the trade-in payment. Because I'm selling the new car, but I'm also buying their old car, right? So I have to subtract the two. Not that we even need to know which one it is for standard deviation, because standard deviation, the variance is always add, no matter what combining we're doing. So if they always add, we need to automatically eliminate B, D, and E, because those are subtracting. So it's got to be between A and C, and just looking at this, you can tell that it looks like it's going to be C, as long as the right numbers are in there. 1,200, and yep. So C is the correct formula. All right. Auditor working for a veterinary clinic calculates the mean annual cost for dogs, and then the mean annual cost for pets in general. Assuming expenses for dogs and cats are independent, so our independent condition is met, right? For those both owning a dog and a cat, what is the mean annual cost of medical care for cats? All right, so that means we're doing pets minus dogs equals cats. They give me pets, they give me dogs, we have to solve to find cats. I'm using subtraction because pets is dogs and cats together. All right, so if I'm subtracting with the means, I just subtract the means. So it looks like the mean for pets is 212, and the mean for dogs is 98. So if I do 212 minus 98, I'm going to get 114. All right, so we're going to eliminate D and E. All right, now the standard deviation, remember, it doesn't matter if we're adding or subtracting. Variance is always add. So I'm just going to put it in this little formula that we proved out last class. I'm adding the variances and then taking the square root to get back to the standard deviation. So it looks like I have a standard deviation of 25 and 39. It doesn't matter what order I drop them in. I'm going to get the same number no matter what because we're adding. So 25 and 39. 25, 39. All right, and let me just prove it to you that I can switch the order. Look, I can, same thing. So we get 46, which is answer choice B. For those of you that selected answer choice C, you must have subtracted. Remember, we cannot subtract with the variances. They always add. All right, number 4 was definitely a challenge question. All right, so number 4, we're combining random variables, and then we're transforming our answer. So boxes of 50 donut holes weigh an average of, so the whole box weighs an average of 16 with standard deviation. Empty boxes alone weigh 1 ounce with a standard deviation of 0.2 ounces. What are the mean and the standard deviation of the donut hole weights? This is confusing because it says donut hole singular, 1 donut hole. We'll come back to that in a minute. Let's see what sort of combining we're doing. So we have full boxes minus the empty box should give us 50 donut hole weights. It's the weight of 50 donut holes together. All right, so remember with the means, we subtract them. So I'm going to take the full box mean, which is 16, minus the empty box of 1, which will give me 15. All right, well, that looks like it's 2 of my answer choices, but look, all of these don't say donut holes, they say donut hole, meaning 1 donut hole. So if 15 is the weight of the 50 donut holes, how do I get the weight of 1 donut hole? I'm going to divide. Remember, if I'm dividing a random variable, what happens to the mean and the standard deviation? We know that the mean always changes, But what about the standard deviation? Will that change with division as well? Yes. The standard deviation changes. Remember, if it were addition or subtraction, the standard deviation would not change. So what I need to do is take this 15 and divide it by 50 and see what I get to get the weight of one donut hole. All right, I get 0.3. So I can eliminate D and E. All right, let's see about the standard deviation. Remember, variance is always add. So I'm going to do the square root of 0.245 and 0.2. So I just dropped my two standard deviations in there. They're being squared to transform them into variances. Then I add them and then take the square root. So let me go ahead and get set up. All right, drop them in, 0.245. Whoa, what did I do there? And 0.2. All right, so that gives us the standard deviation of the full 50 donut holes. So remember, standard deviation changes with division. So I'm going to take this number and I'm going to divide it by 50. Oops, I don't know where those $2 signs came in. Okay. All right, and that gives me my standard deviation of one donut hole, which is 0.0063, which is answer choice A. Now that we went over that exit ticket, let's go ahead and finish the packet from today. So what we did already was we could figure out whether or not something was a binomial distribution based on the bins, right? Binary, independent, fixed number of trials, same probability of each trial. We also went through and did the probability formula for binomial distributions. This is the formula that we went through to calculate the probability of something. All right, now we're going to put that all together with describing a probability distribution of a binomial random variable. All right, how have we previously described distributions? Remember that word describe means something specific in statistics. All right, I hope you said SOC of, right? Which means shape, outliers, center, and variability. We don't do outliers with probability distributions, so all we need to do is address the shape, center, and variability, which we will learn how to do right now. Okay, so the shape of a binomial random distribution is based on the probability of success. So use this little table. If the n is small, and we'll come back to that in a second. All of these are if the n is small. If the n is large, something else happens. But if the n is small and the p is much less than 0.5, it's going to be right skewed. If the n is small and the p is pretty close to 0.5, we'll have a symmetric distribution. And if the n is small and the p is much greater than 0.5, we'll be left skewed. And remember that p stands for probability of success. Okay, let's go ahead and look at our first example. Mr. Hogarth's AP Stats class did an activity to see if his students could tell whether or not they were drinking bottled water. There were 21 students in the class. If we assume that the students in this class could not tell tap water from bottled water, then each one is guessing and there's a probability of 1/3 of being correct. So let X equal the number of students who correctly identify the cup containing bottled water. Here's a histogram of the probability distribution. What probability distribution does X have? All right, so we've talked about binomial distributions, right? So we should probably check for that. We just want to check the conditions. All right, so is it binary? Yes. They either guess that it's bottled water or guess that it's tap water. Bottled water, tap water. Success is correctly guessing bottled water. Is it independent? Yes, I don't see why one student's guess would affect another student's guess. Is there a fixed number of trials? I guess 21. All right, and then does each have the same probability of success? Yes, 1/3. Okay, so we have a binomial distribution. The random variable x is a binomial distribution with n is equal to 21 and p is equal to 1/3. Alright, so when I divide that, I get 1/3 is 0.333. That's not much less than 0.5, and you can see the description, or you can see the shape of the histogram here. It's symmetric. I will say the binomial random variable x has a symmetric probability distribution. Alright, so that was the shape. The two other things that we need to address are the center and the variability, and with all of these probability distributions, we've used the center as the mean and the standard deviation as the variability, which we'll continue to do. So I've got two new formulas for you, but don't worry, they're on the stats formula sheet, and I'm going to get that out soon and get you guys familiar with it. But calculating the mean standard deviation of the binomial random variable. So this should say mean of p. I don't know why it didn't subscript. So the mean, or the expected value of binomial distributions, is just going to be n times p. That's it. Where n is equal to number of trials, and p is equal to probability of success. Okay, we'll calculate that for this distribution in a second. All right, standard deviation, here's our variance. Our variance is going to equal to n times p times 1 minus p. So remember, this is basically probability of success, and then 1 minus p we call the probability of failure. So they add up to 1, right? And then we're multiplying that by n. So if this is the variance, what would the formula for standard deviation be? The square root of n times p times 1 minus p. Alright, our interpretation for the mean or the expected value, we have to mention the groups in. For all groups in, like that's the size, right? For all groups of 21, the average number of context expected successes. So our expected success here is a student identifying bottled water. So we'd say the average number of students correctly identifying bottled water is, all right, so let's go ahead and get some practice with this. So I'm going to go ahead and write the two formulas out here so we can reference them. So mean is going to equal n times p. Standard deviation is going to equal the square root n times p times 1 minus p. All right, we'll come back to that. Assume that each of the 21 students in Mr. Hogarth's AP class who did the bottled water versus tap water were just guessing, so 1/3 of chance, blah, blah, blah. Let x equal the number of students who make a correct identification. Below is a histogram. Calculate and interpret the mean. Calculate and interpret the standard deviation. All right, so let's use this formula. So we need the mean of binomial random variable x And we know that it's just going to be n times p. So my n is 21, and my p is 1 over 3. Let me go ahead and put that in Desmos. 21 times 1 over 3, 7. All right, before we do the interpretations, let's go ahead and calculate the standard deviation as well. So the standard deviation is the square root of n times p times 1 minus p. So I'm going to do the square root of n times p times 1 minus p. There we go. And I get the standard deviation to be, I'm writing this down on the paper, 2.160. All right. I went ahead and did my interpretation. So for the mean, for all groups of 21, we have to state that because it's a fixed number of trials. For all groups of 21, the average number of students correctly identifying bottled water is 7. So I put context in there. I included the mean of 7. All right, for the standard deviation, on average for all groups of 21, so we're saying on average for all groups of 21, the number of people correctly identifying bottled water will vary from the mean, because that's what standard deviation is, right? How far it varies from the mean by 2.160 people. All right, go ahead and try example 3. All right, so I went ahead and I checked my bins, right? B is binary, so you're either male or not male. N is fixed number of trials, which we said was 8 employees selected every month, and then the same probability, which would be 40%. Now, I put a question mark next to independent because you'll notice that we're selecting these employees without replacement. So technically, we violate the I. Let's pause that for a second and just assume that we meet the I condition, even though if you said we did not, I understand why you said that. All right, so we have our success and our failure, our N and our P. Success is selecting a male, failure is selecting not a male, N is 8, and P is 0.4. So I went ahead and plugged in the formula here. The mean is N times P, and I got 3.2. And then the standard deviation formula is the square root of N times P times 1 minus P. I went ahead and just put in the 0.6 because I know that's what has to add up to 1 with 0.4. So just to show you my two calculations, here they are, 3.2 and 1.4. So to round to the nearest tenth. All right, go ahead and try number 4. All right, here's what I got for number 4. It's binary, blue or not blue. I put a question mark next to independent because we're not replacing the candies as we get them, right? So that violates the independence clause, but bear with me for a second with that. Fixed number of trials, 15. Same probability of success, which would be 30%. So I say our success is blue, failure is not blue, our N is 15, and our P is equal to 0.3. So mean is just N times P, and I got 4.5. Standard deviation is N times P times 1 minus P, right? Or N times the probability of success times the probability of failure. So let me bring up the little, those are my calculations. So on average, for all groups of 15, I would expect to get 4.5 blue candies. And on average, in a group of 15, the number of blue candies varies from the mean by 1.8 candies. Okay, so before I told you just to put a question mark next to these I's, and we'll come back to it. So, binomial distributions and statistical sampling. Almost all real-world sampling is done without replacement because it would be completely cumbersome to select someone, put them back in the whole pool, and then do the sample again, right? All these computer algorithms and things like this where we're selecting our random sample just pulls them and lines them up, right? So real-world sampling is often done without replacement, which would technically violate our independence condition. But we have something to get around that. It's called the 10% condition, and we'll be using this a lot in the future. So we have to make sure that this condition is met so that we can say that technically independence doesn't matter and we're good. So when taking a random sample size of n from a population of size n, you'll notice the population is capital N, the sample is lowercase n. We can use a binomial distribution as long as the count of successes in the sample is less, this should be n 0.1, capital N. As long as the count of successes in the sample is less than 10% of the population. Why does this solve the independence problem? All right, think about if you are randomly sampling, imagine a ball pit in McDonald's with a whole bunch of balls in the ball pit. You want to take out 5 balls, and you don't put them back each time when you're selecting. Imagine how big that ball pit is, that when you take out one ball, although it changes the probability of drawing out another ball, it changes it in such a small way because the population is so big and our sample size is so small that it doesn't really matter. So what they're saying is at some point replacement doesn't actually change the probability of selecting the next thing in the sample because the population is so large. And I'll do some more research on trying to figure out a better way to explain that, but for now, 10% condition. All right, so suppose a supplier inspects a random sample of 10 flash drives from a shipment of 10,000. So I know that our sample is 10 and our population is 10,000, in which 200 are defective. Let X equal the number of bad flash drives in this setting. Is this a binomial setting? All right, well, before we do anything, let's go ahead and check the other characteristics. All right, is it binary? Yes, they're either defective or not defective. Is there a fixed number of trials? Yes, n is equal to 10. Does each have the same probability of success, right? And success would be getting a bad flash drive. Yes, the P is equal to 200 over 10,000. Now, technically, if I choose without replacement, I'm not independent, right? But do I meet the 10% condition, which allows me to say I'm independent? Well, let's put it into our little formula right here. N is 10. Is 10 less than 10% of 10,000? Oops, I ran out of paper. Is 10 less than 10% of 10,000? Let's figure out what 10% of 10,000 is. And obviously I can just move the decimal over 1, right? So is 10 less than 1,000? Yes, it is, so I met the 10% condition. So I can say, yes, it's independent. It is a binomial setting. So I'm saying my population is so large and my sample is so small that replacement doesn't even really make that big of a difference. All right, let's go ahead and get more practice with this. All right, in a survey of 500 teenagers aged 14 to 18, subjects were asked a variety of questions about personal finance. One question asked whether teens had a debit card. Suppose that 12% have debit cards. Let X equal the number of teens in a random sample of 500 who have a debit card. All right, explain why X can be modeled by a binomial distribution even though the sample was selected without replacement. Well, is the 10% condition met? Is my sample smaller than 10% of the population? Well, it looks like my sample was 500. And then what would my population be? They don't tell me here. They just say U.S. teenagers, age 14 to 18. So U.S. teenagers. Well, do we think that there are more than 5,000 U.S. teenagers aged 14 to 18? Definitely, 100%, right? So it would have to be more than 5,000 for us to meet the 10% condition. It's safe to say that that population is much larger than 5,000. So the 10% condition is met. because the population of U.S. teenagers 14 to 18 is much larger than 5,000. So our 10% condition is met. Replacement would not really have that much of an impact. We can say that it's a moot point. All right, use binomial distribution to estimate the probability that 50 or fewer teens in the sample have debit cards. All right, well, this is taking us back to what we did in the live session. So I'll give you a minute. You can use Desmos to calculate this. Be careful, it says 50 or fewer, so remember we're going to be using that CDF instead of PDF. So I'll give you a minute to go ahead and put that in. Let's go ahead and quickly review. Does it meet the other qualifications of bins? We already said it met the 10% condition for independence. Is it binary? Yes. Our success is having a debit card, or failure is not having a debit card. Do we have a fixed number of trials? We do, 500. And then is there the same probability of success within each trial? Yes, 0.12. Because it says 12%. So what I went ahead and did is put it into Desmos. Remember, I hit the functions, then went to distribution, and then clicked binomial distribution. I went ahead and put in the number of trials, comma, the success probability, and I clicked find cumulative probability. So my min is 0, my max is 50 because it says 50 or fewer teens, and that gives me my probability. 0.0932, so 9.32%. All right. Okay, so normal approximation of binomial distributions. As in the number of trials increases, the binomial distribution gets close to a normal distribution. Remember, back when we first started the video, we described the shape based on if n is small and whatever the p is. But if the n is big, what's the shape? It's going to be normal. So as n increases, it gets closer and closer to a normal distribution. Why would it be important to know that a distribution is approximately normal? What can we do with normal distributions? We can use our table A to find probability. All right, so what is large? Large is the subjective word. It could mean a lot of different things, right? So since this is a math class, we have to have something objective, an objective test. So this says the probability distribution of X is approximately normal if the successes and the failures are greater than or equal to 10. Then this qualifies for large counts. So you can see the successes is just n times p, and the failures is n times, ooh, that says p minus 1. It should be 1 minus p. My bad. Another mistake. All right, so the expected number of successes and failures are both at least 10. All right, so let's try example 6 with this. In a survey of 500 teenagers, oh, this is the same one. Good, that's easy. All right, justify why X can be approximated by a normal distribution. All right, so does it meet the large counts condition? Let's see, our successes is going to be n times p, and our failures are going to be n times 1 minus p. So n times p, 500 times 0.12. All right, let's see. 500 times 0.12 is going to give me 60. And then my failures would be 440. Both of them are greater than or equal to 10. So yes, I can use a normal distribution because as the number of trials increases, the binomial distributions get closer to a normal distribution. All right, so use the normal distribution to estimate the probability that 50 or fewer teens in the sample have debit cards. All right, so we have a normal distribution. I know that my mean is going to be 60. This is my mean formula, n times p, right? Now my standard deviation, let me go back. We said the mean, I already threw away my old sticky notes. The mean is n times p. The standard deviation is equal to the square root of n times p times 1 minus p. So let's go ahead and figure out the standard deviation. Square root. N is 500. P is 1.12, and then 1 minus 0.12. Alright, so it looks like our standard deviation, we'll round to 3 decimal places, 7.266. Alright. Alright, so if I have that normal distribution, I know that my mean is 60. We're going to estimate the probability that 50 or fewer. So I'm going to draw my line over here and put 50. Should I shade to the left or to the right of 50? I hope you said to the left because it says 50 or fewer. Alright, so now I just need to find this area, or table A value. Remember, you can use the table A or you can use the calculation in Desmos, which is quicker and more exact, so I'm going to go ahead and do that. Alright. So remember, I hit functions, I hit normal distribution, my mean is 60 and my standard deviation is 7.266. I'm going to hit the find the CDF. I'm going to leave my min as negative infinity, and I'm going to put the max as 50 because it's 50 or fewer. So now my probability is actually 0.0844. Alright, so that's pretty close to the original probability we calculated, but this is more exact because it's a normal distribution. So here's our true probability here. Alright.